to solve the problem of this pattern, and all integers, right? When we handle problems in this chapter, all the numbers are integers. Then assume that if the GCD, greatest common divisor of A and B, does not divide C, then no solution. We don't have any solution that satisfies the equation. So I mentioned about this before, because the smallest number that we can get on the right hand side is if it's not 0, it should be GCD, right? The smallest possible number is the GCD. It cannot go lower than GCD other than 0. So if we exclude 0, the possible smallest number on the right hand side should be the GCD. But if C is not divided by the GCD, then we cannot solve the problem, no matter what. So I showed you an example, but if you need more examples of this type, ask me. Do you need more examples of this type? So I will give you one more example. Example like this: 4x plus 8y equals 1. Can it happen? We have 4 and 8, meaning the GCD is 4. No matter what number we use, it should be divided by the whole left hand side should be divided by 4, right? Because of its number. But it is 1. Is it possible? It's impossible, so no solution. So the minimum requirement to solve the problem is this thing. If we cannot divide the right hand side by the GCD, then stop. We cannot find any solution. So I mentioned this last time. And now we will solve the problem if we exclude this case, right? So from this point on, we do not allow this thing. Then what is it? First of all, ax plus by equals C may be satisfied some pairs x0 and y0, right? So assume that this is the solution. Assume that this pair x0, y0 is a solution. So assume that this pair is a solution. Then how can we find more solutions? The answer is very simple. I showed you last time. ax0 plus by0 is C by this assumption. And then now we can multiply AB minus AB, right? AB minus AB is 0. But we can multiply both sides by the same number, T. And then we can divide both sides by same number, G, where G is the GCD. So still 0. Then we can add these things to the top line. Then if we add this, then A and A are common factors. We have A and A are common factors. Then the other terms are x0, and then B over G times T, and then plus B and B are common factors. Then y0 minus A over G T equals 0. So we can get this relation, and last time we arrived at this point. Any questions? Then after this, we want to check the involved numbers. Is this an integer? Because we assume that all the involved numbers are integers. This is an integer. This is also an integer. B is an integer. T is an integer. GCD is an integer. So all these numbers are integers. But we have a problem. B over G exists. B over G. So let's check whether this B over G itself, the fraction itself, is an integer or not. So what is your guess? Is this an integer or not? Yes?
Can the equation be able to C?
Thank you. So is this an integer or not? Yes, why? Because G is the GCD or CD divisor, right? G is a divisor of B, right? So B is divided by G, that means this is an integer. What about this number then? Is this an integer? Yes, so we are done. So now we can find all solutions. So x is equal to x0 plus b over g times t, and then y equals y0 minus a over g times t is the solution, right? So there are infinitely many solutions as we vary t. T is equal to 0, then we get one pair. T is equal to 1, then we can get another pair. T is equal to 2, we may get more pairs, right? So we get many, many pairs of this pattern. So instead of just using letters and symbols, I will give you some example, but instead of giving you my own example, I will let you create your own. Then you will know that it works no matter what. So let's try. So what number would you like? Any 2-digit or 3-digit number will be welcome. 1, 2, 7, right? And then what number do you like? 2, 7, 1. And then what number do you like? 1. So I want to solve this problem, but if you don't like, I will change. So you may want to change, then I will change. Then let's find x0, y0. So first step is find x0, y0. To find x0, y0, use Euclidean algorithm, right? Euclidean algorithm. So by Euclidean algorithm, we write it 2, 7, 1, 1, 2, 7. Then 2 is good, right? 2 is the quotient, right? 2 is the quotient. Then multiply 2, then 254. We subtract 254 from the top, then 7, and then 17. Do you get it? So if you don't have any problem with this number, then I will continue. If you divide this number by 17, then what could be the quotient? About 7, right? About 7. Then 17 times 7. 17 times 7 is 17 times 7, 49. 1 times 7 is 7, then 9, 1, 1, right? So 1, 1, 9. Subtracted from the top, then it should be 8. And then we use 2. Then 16 subtracted, then we get 1. And then 8. 1 times 8 is 8. 8 subtracted from 8, then 0. So what is the GCD of these two numbers? What is the GCD? This one is the GCD. This means we have a problem that has a solution. If this GCD does not divide the right side, then we don't have any hope, right? But luckily we have one dividing the right hand side. So I could get this number, and if you have a question about this Euclidean algorithm, ask me. Then the next thing is writing this portion 271 times y, right? 271 times y. So y position comes here, and then 127 times x, right? So we have x position, and then we have 1 and then 0. Because 1 times 271, 0 times 127 is 0. Do you follow me? You already know this. And the same thing. Any questions? Then we do the same thing in this column and in this column. We did something here, and we do exactly the same thing to these columns. So we multiply this number and subtract. 0 subtracted, 2 subtracted, and then 7 subtracted, and then negative 14 subtracted, and then negative 14 subtracted, and 30 subtracted. So I got this number. So I did the same thing in each column, but if you don't understand, ask me. Yes? So what part do you want me to go through? The one, this thing? X? So we subtract this number from 0. Then it is negative, right? And then we subtract this product from this, then 15, right? So we subtract this product from this number. So we do the same thing here, right? We subtract this product from this thing. We subtract this product from... We are using division algorithm over and over again. So we subtract this product from this, subtract this product from this, subtract this product from this, and so on. So do the same thing over and over and over again, right? Anywhere. So this led to the solution. What is y? Y should be equal to what? Y should be equal to 15. X is what? Negative 32. Then the right hand side is what? 1. So we got the solution. So x0, y0 is found. So Euclidean algorithm is the first step. And the second step is 2 more columns, right? 2 more columns. Right? 2 more columns. Like operation. And then afterwards, third step is determining x0, y0 pair. So in this case, y0 is 15, right? y0 is 15, x0 is negative 32. Then we are ready. But the question is not just one solution. But at least let's check whether this solution is correct or not. So let's check it. We have 1, 2, 7, 2, 7, 1. So 1, 2, 7, 2, 7, 1. And then I want to check whether this really is equal to 0. So let's do it. Oh yeah, 1, sorry. 1 to 7 multiplied by 32. So I will do the calculation, and I'm showing you the method of multiplying these numbers. So on the exam, you are not allowed to use your calculator. Then what else can you use? This thing, right? So 7 times 3 is 21. 2 times 2 is 4, right? If we blanket, it is 0, right? 1 times 2 is 2. Then 1 times 3 is 3. 2 times 3 is 6. 7 times 2 is 14. So I wrote down all the necessary ingredients, right? Any order is okay, right? I wrote down. Then it's time to add these numbers in slant direction. So we add in slant direction, right? Slant direction. So let's add them. Then this is equal to 4. And then 1 plus 1 plus 4 is 6. 2 plus 6 plus 2 is 10. And then 1 plus 3 is 4. Do you follow me? So this is 4064 with negative sign, right? So please do the right hand side to practice. So you should check whether your solution is correct or not in each step. I intentionally commute these things. (15 to 7, 1). I completely showed you. I didn't use any calculator. I completely showed you. If you do not know why this is so, ask. So on the exam, no calculators. You should calculate every multiplication on your own. In any case, I verified this result, right? Negative 32, 15 is a solution. Now, I want to find all the solutions, not just these things. So what should I do? I use this idea. Solution plus the other number divided by the GCD multiplied by T, right? And then solution, because I added, I should subtract, right? You now know the reason, right? If I just add, then we can have 0. We should subtract to get 0. So this is the reason why when you have plus here, we should have minus, and vice versa. When you have minus upstairs, then we have plus. So the other number should be used. So x equals this number, negative 32, plus the other number, 271 divided by the GCD multiplied by T. Do you follow me? And then y equals 15 minus the other number, 127 divided by the GCD multiplied by T. Then done. So all the solutions have this pattern. So you may pick T which is not very big. Then I will verify this thing. So pick one digit T, one digit number T, then I will verify whether the pair is a real solution or not by just purely multiplying. So please pick one T. If you are not sure about other T's, then I may pick one more, but please pick one digit number. What is it? Any positive or negative one digit number is okay. 3. I didn't pick this number. Someone picked the number, the 3. So if T is equal to 3, what happens? If T is equal to 3, then x equals x0 plus 271 multiplied by 3, right? And then y equals 15 minus the other number, 127 multiplied by 3, right? I said this is a solution. So let's check whether this is really a solution or not. So let's do it. If we calculate this thing, then 271 multiplied by 3 equals 1 times 3 is 3. 7 times 3 is 21. 2 times 3 is 6. Then 3, 1, 8, right? Do you follow me? So 8, 1, 3 is the number that we multiplied. Minus 32 equals 1. And then 8, and then 7. So it's 7, 8, 1, right? 7, 8, 1 is the result. Let's calculate the other number. If we multiply 1 to 7 by 3, then 21. And then 6, and then 3. Then add 1, 8, and then 3. So 3, 8, 1. 3, 8, 1 minus 15 equals 4 subtract 6, right? And then 6. 366, so it's negative 366. Any questions? So I got this result. And let's check whether this is really a solution or not. So I want to claim this thing. 1 to 7 multiplied by 781 plus 271 multiplied by minus 366 equals 1. This is the one I want to show. Before beginning to calculate, if you have a question, ask me. If you don't, then I will begin to calculate to show you. Yes?
Why do we need to apply GCD?
Because if we don't divide, then we skip some numbers, right? This jump is too big. But if we divide, then we find all the possible jumps. We don't want to miss anything. Yes. So let's do it. So it's a big chart, right? I will do one thing and then leave the other for you. So it's a big thing. that we need to create 1, 2, 7 multiplied by 7, 8, 1. That is the one that I will do. I don't even want to subdivide, but for the purpose I will subdivide. So let's do it. Any order is okay. I will do the middle one, 16, right? Any order is okay. 1 times 1 is 1. Any order is 7 times 49. Any order is okay. 14, and then 7, and then 56, 8, and then 2, 7. Any questions? Then it's time to add 7, 8, and then 10, and then 11 more, 21, right? So 2 added, right? So 2 plus 8 is 10. So it is 8, and then 1, 9, right? I got the result. 9, 8, 1, 8, 7, right? You need to read it this way, right? This order, right? You need to read it in this order. If you don't follow me, ask me. Yes? 9. Oh, I missed this number. Sorry, I didn't see the number. Thank you. So something was hidden behind. I didn't see. So 9, 9, and then please calculate the other number to practice. So I will give you about 1 minute. You can do it in 1 minute. I got the result, right? I showed you. In other words, what we developed is not just for just one solution. It's not just a lucky break. What it did was very, very systematic. It finds all possible pairs. All possible pairs. I examined it with 3. But T could be any number. T could be, for instance, 1 million. So to verify this statement, instead of doing hand calculation, I will use MATLAB, which is not allowed on the exams, right? But I will use it anyway because I want to show you whether this is really true for any number. So it's like this. So let's do it. So if we multiply, first of all, t equals 3 is the statement we used, right? T equals 3. And then x equals negative 32 plus 271 multiplied by t, right? And then y equals 15 plus the other number, 127 multiplied by t. And then what he did was this one. 8, 127 multiplied. Thank you. Thank you. Then what he did was 127 multiplied by x plus 271 multiplied by y. That was the thing we did it, right? Y. This is the thing we did it, right? Do you follow me or not? So let's verify these things with other t's. So I will vary t. T was 3. You may pick any number because I have MATLAB. You can pick 3-digit numbers if you want. 4, right? So I just pick this number, right? So I pick this number. Then now I will calculate x. X is this one, right? Very big. And now I will pick y. Y, right? So x is chosen, y is chosen. Then let's examine it. 1, right? So no matter what t is chosen, we can determine x and y, and then eventually we can determine the solution. So one more time. You may pick t big enough. So what t do you want? I will pick minus number. Negative, right? So I chose this number. Then what is x? X equals this, right? And then y equals what? This. And then what is the result? 1. So no matter what t is given, we can find it. And someone asked about the reason why we are dividing by the GCD, because if we don't divide by GCD, it's a solution. I'm not meaning it's not a solution, but we may jump some legitimate ones because we didn't divide by the GCD. We jump too much. Do you follow me or not? So I will let you know the reason because you saw the result. So take a look. Assume that we don't divide this by GCD. Then these are added to this result, right? Then if we add these things, then we get a multiplied by x0 plus bt, and then b y0 minus at equals c. We get this, and then x is this one, and y is this one, and there is no problem. This is a solution. But does this cover all possible solutions? The answer is no. It misses something because we didn't refine it. So I will describe the situation. Solution may exist like this, right? Solution may exist like this in the x direction, and then the y direction is similar, right? Solution may exist in this direction, but if we don't divide this by the GCD, then we miss many terms, and we just find this number, and then next to this number, and then next this number, and then next this number, and so on, by missing these things, by missing these legitimate solutions. This is the reason why we must divide by GCD. Do you follow me or not? You may wonder why I divide the number by GCD. Then can you refine further? In other words, can you divide by bigger number? GCD is the limit, because if we divide this by some number bigger than the GCD, then the divisor is not the denominator is not the GCD of this number anymore. It means we cannot get an integer. So this is the maximum possible number that we can divide, right? So to avoid this problem, we use GCD. So to avoid this problem, we divide by GCD, then it jumps to these things, right? All the numbers. So this is the reason why we divide by the GCD. So now I completely covered all the possible cases. The bad case that doesn't have any solution, right? The bad case. And the case that we can use Euclidean algorithm, and then finding all possible solutions without jumping too big, right? If we don't divide, then it's too big. I completely finished this section. But if you still have a question, ask me. If you don't, then I will go to the next chapter after a brief summary, because some statement will be used in the next chapter. Do you need more examples, or these are enough? And then you can continue. So let me know. Then let's handle some bigger problem. Instead of just going to the next chapter, let's handle some bigger problem. So I will allow you to use bigger numbers. So what problem do you want to solve? Anything I didn't set up, so you can just ask anything. What number do you like here? Seven. Anything is okay, so please pick. 7 and what? 9 and then what? 3. The next number. What number do you like? Any number is okay. 8, right? So this is the one we want to solve. First of all, whether we should check whether it has a solution or not. To do it, all we need is a Euclidean algorithm. So 2, 9, 7, 2, 7, 4. And Euclidean algorithm is nothing but the division algorithm. So I want to divide this number by this one. 3 is too much, right? 3 is too much. If I divide this by 3, then it's too much, so 2. Do you follow me? Quotient is 2. It's simple algebra, right? So 2, 7, 4, multiplied by 2, it gives us 8, and then this gives us 14, and this gives us 4. So total is 8, 4, 5, right? 5, 4, 8 subtracted from this number. 5, 4, 8 subtracted from this number gives us 5, and then 4, and then 2, right? 245. Then 245 subtracted, then it is, the quotient is 1, and then subtraction gives us 9 and 2. And then I want to find appropriate factor. About 8 will be enough, right? 8 divides, so 29 multiplied by 8. Then 232, right? 232 subtracted. Do you follow me or not? So 232 subtracted from this number gives us 3 and then 1, right? And then 26 subtract 3. And then 4. It's just calculation, so I don't want to spend too much time, but if you don't follow me, you can ask any part. 0. So what is the GCD? 1. So is this problem okay? Yes, this problem is okay. This problem is okay because the GCD divides the right side. If the GCD does not divide the right hand side, dead end. Just stop there and say there is no answer. If there is any mistake that I made, or if you do not follow, ask me. Any questions? Then let's find the number making 1. So some combination makes this 1. So let's find those numbers making this equal to 1. So to do it, I will begin with 1, 0, 0, 1 column, right? And then let's finish this column. Multiply and subtract. 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 How did you do it so fast? This I'm not good at addition, so let's do it slow. You're right, right? You're right. And do the same thing to the other column. I found this number without using any calculator. If you don't follow me, ask. So let's check it, but instead of doing hand calculation, I use MATLAB. So MATLAB can easily calculate it. 85 multiplied by the top number, that is 793. 793 plus the other number is 274. 274 multiplied by negative 246, right? Do you follow me? So 793 and the solution x85, and then 274 multiplied by the other solution, then it is equal to 1, right? Then, now how can you make 8? How can you make 8? Multiply everything by 8, right? Multiply everything by 8. So I multiply 8 here, then we get 8, right? If I multiply 8 here, then what do you get? So 85 multiplied by 8. Then 680, right? 680. 680 is the result. If you multiply this by 8, if you multiply this by 8, 48. What is 4 times 8? 32. 16. Then it is 8, and then 6, and then 9, 1, right? So negative 1968. So I just multiply this row by 8. So I just did the same thing to the equation, right? The equality, and I got this pair. So x0 is 680, y0 is negative 1968, right? So this is x0 and y, and then now plus the other number over GCD. The other number is what? The other number is 274, right? So 274 divided by the GCD, multiplied by t, and then this minus the other number, 793 by the GCD. So this is the solution to the problem. this is the solution to the problem, and check it. Did I use any up to, except the verification, did I use a calculator or a computer? No. Only to verify I used a calculator or the computer, but I derive everything by hand calculation. So with this method, it's not very difficult, but without it, if you can find it, find it. On the exam, if you don't use my method and find it, it will be great. I will give you full credit. So it's not easy to guess this kind of solution, right? Is it possible to guess these solutions on the exam? You may waste 3 hours for the final to solve this one problem and couldn't get the result. Cannot get the result, right? It's possible to solve the problem any way possible. Do you need more examples, or this is not?
Why is the GCD there 1?
GCD, it happened to be 1. It shouldn't be, but it happened to be 1. These two numbers are given, and then this GCD happened to be 1 because of this calculation, right? We arrive at this point, and then we got 0, right? So the number above 0 is the GCD. So GCD happened to be 1. Do you follow me?
And we're trying to find it for 8, right?
The question is for 8, but in any case, we should find the GCD first. So we should find the relation leading to the GCD, and then we multiply this equality by 8. I will write down the meaning of this. I wrote down the meaning before, but I will rewrite it. It doesn't hurt. So what is the meaning? It's the meaning. So meaning of this line is what? I abbreviated so much, and someone may lose the meaning. So 1 equals the first number, 793 multiplied by 85 plus 274 multiplied by negative 246. This is the meaning. I used the abbreviation because I don't want to carry equal symbol, this number, parentheses, this number, these things. I just shorten the expression to write this kind of row. Then, now we have 8. Then what should we do? We have 8. Then I should multiply this by 8. Right? I should multiply this by 8. And then I should multiply this by 8. Do you follow me? This is the reason why I got this kind of things. So I just multiply this and numbers by 8 to make these things equal. Any other questions? Because this is the end of the story. After this, you should be able to solve all the problems in the book or anything of this pattern, right? Anything of this pattern should be solved after this, right? So if you have a doubt or questions, ask. Then next chapter. So I will summarize this chapter 2 so that I can use some fact in chapter 3. So let's briefly summarize. The biggest thing is the division algorithm. If you divide A by B, then you can get the quotient and the remainder, right? Remainder happen to be between 0 and the number less than B, right? So this is the division algorithm. We are not worrying about fractions or real numbers. We are using just integers. Everything here is integer. But as I mentioned before, this stacking is not very efficient, right? This stacking is not very efficient. Nor this stacking is not efficient. We cannot even stack. Once we multiply B and Q and subtract, then we get A minus BQ, which happen to be R, right? But after this, how can you stack? So because of this deficiency, we don't use the first stacking or second to stack, right? We don't use first one or second one to stack. To stack this thing, we completely reverse this thing. If you divide A by B, then the quotient is Q, and the remainder is this A minus BQ, that it happened to be R. And then here, I wrote down the full description, but in the end, only thing that survives is R, right? So we will just say R. For the description, I wrote down A minus BQ, but once we calculate, we get some number called R. So this way, we can stack. Do you see the reason? You should see the reason. Why do we handle these things? Because I want to stack. If I don't want to stack, top one works nice, or even this one that you learned, this long division that you learned in elementary school is okay. But with this, how can you stack? So to stack, we do this division algorithm. So what is it? If you have A divided by B, then the quotient is written on the left side, right? Quotient is written on the left side, and the remainder is written here. So this is just one division algorithm. Stackable division algorithm, right? And you can stack these things to make Euclidean algorithm. Then what is the key? If you divide A by 2, then what is the key? If you divide A by Q, then A by 2, then either 0 or 1, right? This is the key. If you divide some number by 2, then either the remainder is 0 or 1. If you divide by 3, then 0, 1, 2. This is the key that we use to prove many things. So prove that something is a multiple of 3. Then you divide some number by 3, and then the remainder could be 0, 1, 2. Do you follow me? So this is the key thing that you need to use in division in many proofs. So division algorithm is everything in chapter 2, right? This is everything in chapter 2. Then a few proofs such as this. I don't want to reprove it, but important facts are these. Assume that A divides C and then B divides C. Both A and B divide C with GCD, so plus GCD of AB equal to 1. So assume that you have this condition. Then what kind of conclusion can you get? Can you get more powerful conclusion? The answer is yes. If this happens, then A times B divides C. So we can get more powerful conclusion. You may wonder, what about the other direction? This direction is very nice, right? What about the other direction? Can you show the other direction, or the other direction is trivial, either of the two? Can you show the direction, or the other direction could be very trivial? So what is your guess? The other, in other words, if AB divides C, then A divides C, B divides C. What is your guess? Is it true or not? If A times B divides C, then A divides C and B divides C. So is it true or not? It's true, first of all. And is it trivial or not? It's very trivial. Why? So here, the conversion. Something divides something can be rewritten. This is very inconvenient to use. So I use this is equal to this number multiplied by something, right? So this is the key you should use. So this divided by this is written in this form. So let's do it. What is this thing? C is equal to what? AB multiplied by something, right? C is AB multiplied by something. What is this? C is A times something, right? And what is this? C is B times something. But already you find A and B here. So this direction is very trivial once we write this way. Do you follow me? So the other direction doesn't cut. In other words, there is no theorem or corollary or lemma mentioning the other direction, and you should know the reason. Why? It's too trivial. Do you follow me? The other direction is too trivial. Because if AB divides, then you can see the A factor and the B factor that is required in the process, right? So this is one lemma that we need in the next chapter, right? This is the lemma that we need in the next chapter. The next thing is similar. if A divides B and C with the condition GCD of AB equals 1, then A divides C. What about the other direction? Is it trivial or not? The other direction. Like the previous case is too trivial, right? The other direction is too trivial like the previous case, so we don't even consider. Do you follow me or not? The other direction is too trivial. If you want to verify it, you should translate this into equality language, right? So translate this to equality language, and you will clearly see that the other direction is too trivial. So I already proved it, so I don't want to prove it, but this will be used frequently. So we considered many cases having products. So it's called Euclid lemma, right? Euclid lemma. In other words, if A divides product, then something should be divided. Some factor should be divided by this A. This is the case. The other direction is too trivial, so it doesn't cut. So I will pause, and then you can check whether the other direction is really easy or not, or this is true or not. So please check all these things, because we will use this thing in the next chapter. Then finally, Euclidean algorithm. Under this statement, when this happens, the GCD of A and B shouldn't be found in A and B form when these number A, B are too large, right? When A, B are too large, then finding the GCD is very difficult. So this is the key proof of the Euclidean algorithm. This statement is the key proof of the Euclidean algorithm, saying it is GCD of what and what? What and what? B and R. This is the key leading to the proof of the Euclidean algorithm, right? So this is the proof of Euclidean algorithm. Because of this fact, we can now stack. Stacking this division algorithm is meaningful because of this reason. In other words, once you are asked to find the GCD of A and B, you should not worry about big numbers A and B. You should worry about B and R, right? So this is the key leading to the Euclidean algorithm. So whenever people asks you why Euclidean algorithm works, you should say steep, right? Steep. And then why? This is it. Because we can repeat these things over and over and over again until you reach the end, right? 0. You can do these things over and over. So this is the reason why Euclidean algorithm works. This is the proof of the Euclidean algorithm. So take a look. Assume that you are asked to find the GCD of these things. Right? And then assume that you are asked to find the GCD of these two things. You need to find all the factors of first number and all the factors of second number, and then find the common divisors, and then multiply the common divisors to make the GCD in usual process. Do you follow me? But now, no, I want to be smarter with number theory technique, and number theory technique said, oh, if you divide this by this number, then the quotient is 1, the remainder is what? If you divide this by this one, the remainder is what? So, because of this reason, it is the GCD of this number, and then 1. Right? Then, GCD of 1 and other number is always 1. So, done. It's a huge difference. Even though you may think it's trivial, it's huge difference. Because of this reason, we can use Euclidean algorithm. In other words, as I mentioned before, some programming task asks the student to find the divisors. Then they find all the possible factors up to square root of this thing. So we divide by 2, 3, 4, 5, and so on up to the square root of this thing. If the instructor is smarter, then the instructor may ask you to jump by following just prime numbers. Smart. But if you use number theory, it's way easier. You don't have to find all the factors of this thing and all the factors of this thing to find the GCD. You can use the division algorithm and then find the GCD of this smaller number and the remainder, which happen to be 1. Then it's very easy. You should clearly see the reason why we are proving small facts called theorems or lemmas. By accumulation of these small things, we can create this very powerful algorithm that is used where, without using these things, you cannot live in modern society. First of all, your TV, your internet images, your cell phones use these things. All has this Euclidean algorithm embedded. Then let's go to the next case. So with the proof, now we can stack. So no matter what two numbers are given, we can do it. So I will pick some small number, 37, and then 16. Assume that we have these two numbers, then we can do the division algorithm. Then quotient is 2, then 32 subtracted 5, right? So this is the division algorithm applied one time. And now, because of the previous fact, we can do the same thing with these two new set of numbers, right? These two new set of numbers. Then we can get 3, then 15 subtracted 1, right? You can multiply 5 and then 0. Once you see 0, the number above 0 is the GCD. GCD is 1. So this is the reason why Euclidean algorithm works. And where is it? The key idea is this. The key idea is this one, right? It's very, very important idea. Without this thing, I may ask a question on the final exam and use anything possible to find the GCD of two big numbers. If you use this algorithm, it's very trivial. And if you use this fact, it's trivial like this. But if you don't use this thing and find all the factors, then you may spend like 4 hours to find the first factors. First factor requires about 4 hours, right? Find all the factors. So this is it. Then with this thing, we can salvage something. And the idea is writing this thing with tautology, right? It's the same thing. Why do we write these things, right? It's trivial thing, right? 37 is 37 plus times 1 plus 0. Trivial thing. And then same thing, 37 multiplied by 0 plus 16 times 1. Trivial thing. But math is not magic. It is the stack of small ideas. So we add and subtract equalities. So we can add these things, multiply to everywhere in the equality, and subtract, add. We can do all these things, right? I already described. So we multiply this thing everywhere in the second equation and subtract. Then what do we get? If we subtract, then we just multiply, then subtract, right? And then 16, and then 0, and then we subtract this product 2, right? So I just multiply the second line by 2 and then subtract it from the first line. That is written here. And then we can do the similar thing, but before going further, we can simplify the result. This is 1, this is negative 2, right? Then the next step is we do the same thing, right? We multiply this by 3 everywhere and then subtract. Then we get negative 3, and then we get 7, right? This happens to be equal, right? Because we are handling equality, it should be equal. But because of the inconvenience, we extract necessary columns. So what we extract is the column involved in the GCD calculation, right? This is in the GCD calculation. And then quotient, right? These quotients column are used. And then 37 is everywhere, so I don't want to write. I just write this portion, this column, and then this column. So by just writing these columns, we eventually solve the Diophantine equation of ax plus by equal to c. Then finally, we can generalize these things with this thing. When you have Diophantine equation, ax plus by equals c, then if GCD divides, GCD called the G, right, divides C, then the solution is any solution, x0, y0 pair, found by this kind of method, plus, minus, the other number, b over gt, and then the other number, a over gt. This is it. Then we find all the solutions to the Diophantine equation. So this is the end of chapter 2. Then I will overview chapter 3 for about 50 minutes, unless you have a question about chapter 2 problems or theories or techniques. The next thing is way harder than first two chapters. So number theory course is very tough because it stacks vertically. It doesn't allow you to relax. If it is vertical, you have a lot of empty space that you can enjoy, but we don't expand horizontally. We go straight up, up, up. So chapter 3 is an example. From chapter 2 to chapter 3 is a huge jump. So essentially, we are handling prime numbers, or prime itself is a noun, right? Prime itself is a noun. A prime or prime numbers. So what is prime number? 2, 3, and 5, 7, and then 8, 9, 10, 11, and then 13. These are called prime numbers, and the rigorous definition is written in the book. And the divisor of this number should be itself or 1. Itself or 1, excluding 1. 1 is not prime by definition. So divisor is either itself or 1. Then it's called prime. 1 satisfies the same condition. Divisor 1 is 1 or itself, right? Why is 1 excluded? Because all prime numbers have two factors, 1 and itself. But if we include 1, then 1 is the divisor, and then 1 itself is the divisor, means only one divisor. Then we cannot systematically build theories, because prime number should have only two divisors, itself and then 1. Do you follow me? So when they defined, in the past, even 2 was excluded. In the past, people called primes from 3. Only odd numbers were prime. But later they included 2. Then there is a question, how many primes are even? 1, right? Only even prime is 2. Why? Because if we have bigger numbers, such as, for instance, 10, then 2 multiplied by something, right? Then there are more than 2 divisors. Do you follow me? So the only even prime is 2. So in the past, even 2 is excluded when people defined prime number. So from 3 to something was. But in any case, this is the definition part. And historically, there are something. If you are interested, you can ask. Then I will email you the link to all the descriptions. Then what is most important thing most important thing is called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Free trade agreement tools. So fundamental theorem of arithmetic is what? If you have some number, pick any number, 24, then 24 is multiplying 2 how many times? 2 times 2 times 2, 3 times, right? And then 3, 1 time, right? So this is the fundamental theorem of arithmetic. If you hear about fundamental theorem of arithmetic, you might be scared because fundamental theorem, but it is this. The fundamental theorem of arithmetic is this thing. If you have a number, then you can find the prime factors like this, right? 2 and then 3. By using prime numbers, we can decompose. This is called the fundamental theorem of arithmetic. So this is the key thing that we will encounter. And the next thing is, how many prime numbers? We can write prime numbers, then really stop at some point. In other words, this is the finite prime number, or we cannot stop. That is the next question. So what is your guess? You cannot stop. So this does not stop. It continues forever. It continues forever. So that thing will be considered. And then question is not the fact itself. Of course, knowing the fact is important, but the question is the proof, right? Prove that there are infinitely many prime numbers. That kind. Then, how many is also a question. How many? And this shows the infinity. And pattern. Pattern is the question. Can we have some kind of pattern of prime numbers? And, for instance, 4k plus 1 type prime number, or 4k plus 3 type prime number. Do you know what I mean? The prime number happened to be 4k plus 3. So can you find many prime numbers of that kind of pattern? That kind of thing. So as I mentioned before, this section is way different from previous two sections. Then, instead of scaring you too much, I will begin with very simple thing. So I will be very slow from this chapter. Especially chapter 3 and 4, I will be extremely slow because I do not know the design of this book, but they made these things very early and then compact. Some instructors cover this too fast, then students are completely lost in chapter 3. So instead of letting you have difficulties too much here, I will try to be very, very slow. So cover and then explain, and everything will be repeated. So definition part is already done, and the next thing is the theorem. It is almost the same theorem that I explained. If the theorem 3.1, if P is a prime then, and P divides A and B, then P divides A or P divides B. The other direction is trivial, right? The other direction is trivial. So, check it. Can you see the similarity of this one and the one that I reviewed? What is the lemma that is related to this thing? I reviewed the previous chapter. When I reviewed, I mentioned about two cases. And what is the lemma similar to this thing? Euclid lemma. So let's return back to the situation. I wrote down two cases. A, B divides C with GCD condition, right? With GCD condition. Then A, B divides C. This is the one, first statement that I mentioned, right? But this top case is not this case. The next thing that I mentioned is this thing. If A divides BC, and then GCD of AB is not 0, then A divides C, right? Do you remember this thing? So this thing is very similar to this thing called Euclid algorithm. Do you follow me or not? This is nothing but Euclidean algorithm because GCD of, I will write the situation. Assume that the GCD of the divisor P and A is not equal to 1. Then the prime numbers have only two possible divisors. What and what? 1 and itself. So if the GCD is not 1, then what is the GCD of A and P? In this case, A and P is P, right? Then GCD of A and P is P means P divides A. So done. Do you follow me or not? If you don't, then I can slow down. But if it's not the case, in other words, if GCD of A and P, if GCD of A and P is equal to 1, then because of this Euclid lemma, what can you say? This P should divide the other number, right? If it doesn't divide the first number, it should divide the second number. This is the key of Euclid algorithm. It is exactly the same. So it's nothing but the Euclidean algorithm. I mean, Euclid lemma, right? Euclid lemma. This is nothing but this Euclid lemma. So instead of worrying about the details, try to understand the meaning. If P prime number divides a product, then it should divide something in the product, right? Some factor in the product. So product consists of factors, right? If prime number divides the whole thing, then it should divide one specific thing at least. So this is the key. And generalized thing is this. If P divides N1, N2, N3, N4, N something, right? Product of these things, then P should divide something specific here, right? Then P should divide N something, right? Something should be divided by P. And using this, we lead to the fundamental theorem of arithmetic, but we don't have enough time. So let's stop here, and you may ask questions. If you didn't submit, please submit the homework.